And welcome back, everybody. We are in Chapter 3, Section 6, Mathematical Models, Building Functions. In today's lesson, primarily what we are working on are word problems. So let's take a look at what we have. So in our first example, find the distance from the origin to a point on the graph. So if we remember back our just regular XY grids, where they cross the X and the Y axis is called the origin. And so it's that point there, and that is the point 0, 0. So that's what we're going to go to. We're going to go from that point to another point. So as we take a look at our information, let P be the point xy, be a point on the graph of y equals x squared minus 1. Our very first set of directions then says to graph that graph. So let's see, if we go ahead and take a look here, here's our x and y axes. And if we had just y equals x squared, so if we had y equals x squared, then it would just be a U shape, and it would go through the origin. What this minus 1 does for us, if we remember from our transformations, that is going to drop our axis, drop our points by 1. It's going to slide everything down. So normally we would have been at 0, 0 as our vertex. Now we're going to be at 0, negative 1. 1 to the side, normally our squared function with 1 squared is 1, but we're dropping it down 1, so it puts it at 0. And 2 squared would be 4, dropping down 1 would put it at 3. So 1, 2, 3. And of course we have the symmetry on the left side and the right side of the y-axis. I missed my point there just a little bit. See if I can't do slightly better here. There we go. All right. So it's like slightly off on the right side there, but we get the general idea. So here's our graph, and what we want to do is we want to say, okay, let's take some generic point. Let's take a point xy on that function, y equals x squared minus 1. Let's take the origin, and then we want to calculate what is the distance between those 2 points, wherever that point is. So it might be over here, might be up over here where we calculate that distance. Just, it doesn't matter where it is, we just want to be able to go ahead and calculate that. And so that's letter A, and then the rest of it is express the distance from point P. So point P was this one here, just our generic xy, to the origin as a function of x. So if we go back and remember what our distance formula is, our distance formula was x2 minus x1 squared, so the difference in the x coordinates, plus the difference in the y coordinates squared, and then the square root of that. So what we will do is we will let 0, 0 equal x1, y1, and we will also let just the generic point P. So there's the O for the origin, P for our point, and we'll let that be x2, y2. Now our formula ends up becoming, let's see, x minus 0, quantity squared, plus y minus 0, that quantity squared. So our distance then is the square root of x squared plus y squared. Okay. Now what we were asked for in our question, if we take a look back at the top of the screen there, express d from P to the origin as a function of x. So we want to write this only in terms of x. Well, fortunately, as far as our y here, in our y squared, we already know from the top that y is the same as x squared minus 1. So what we can do then is we can replace this y squared with x squared minus 1, and then come back and fill in the rest of everything else. Now this is only in terms of x, so we can say this is now a function of x. So we have the distance in terms of x is x squared plus x squared minus 1. We may want to go ahead and clean that up a little bit. I forgot one small piece here. It's x squared minus 1 squared. Okay, forgot my square. So we might clean this up just a little bit, and let's take a look at that. So we will end up with x squared plus, and then x squared minus 1 multiplied by x squared minus 1. That's the definition of a square. Let's see, we have x squared plus, First terms, x squared times x squared, x to the fourth. Outside terms, minus x squared. Inside terms, minus another x squared. Last terms will be plus 1. So then we have our distance formula now. We combine everything. We've got x to the fourth. So we've got x squared minus x squared, and then a minus x squared again, plus 1. So this is our final formula for the distance between any point on the grid, or any point on the parabola y equals x squared minus 1, and the origin. So now we have that graph. What we're asked now to do is figure out, okay, well, what is the distance when x equals 0? So when x equals 0, well, on the graph, we would be here. We would be at 0, -1. Well, the distance from the origin down to 0, -1, that distance should end up being 1. Let's go ahead and calculate it and see if we end up with the same thing. So for part B, we're saying if x equals 0, find d. Okay, so d of 0 is going to end up being the square root of. Previously, we had our formula down here as x to the fourth minus x squared plus 1. So it's going to be 0 to the fourth minus 0 squared plus 1. So d of 0, see, 0 to the fourth is 0, 0 squared is still 0, plus 1. So the distance when x is 0 is the square root of 1, which is 1, which is what we thought it would be from our graph. Okay, let's take a look at letter C. C says, what is the distance if x equals 1? Well, from our graph, if x equals 1, we're at this point here. That's the point 1, 0. So the distance from the origin to the point 1, 0 should also end up being 1. Let's go ahead and calculate it, though. So if x equals 1, let's find d of 1. So d of 1 now is 1 to the fourth minus 1 squared plus 1, square root the whole thing, doing some substitutions. So we end up with 1 to the fourth is 1 minus 1 squared, which is also 1, so that goes to 0. And then plus that 1 is 1. Square root of 1 is 1. So the distance, as we thought it should have been, is indeed 1. And then our last example in this particular case, we're asking what is d if x is the square root of 2 over 2. Okay. So now we want to find d of the square root of 2 over 2. Okay. Well, distance evaluated at square root of 2 over 2 is going to be the square root of 2 over 2 to the fourth minus the square root of 2 over 2 squared plus 1 square root of the whole thing. So that gets a little more intriguing because we got some interesting powers. So what we can do is I would rewrite this square root of, square root of 2 squared and then squared. That was get us our fourth. And then minus the square root of 2 over 2 squared plus 1, square root that whole thing. And then what I would do then is I would calculate this value. The square root of 2 over 2, that quantity squared, is going to be the same as the inside over here. Then I can go ahead and apply that other square on it. So this is going to end up as, let's say work the one on the right here. Square root of 2 squared, the square root and the square cancel, so that's just 2. And then 2 squared is 4, so that's going to be 2/4. So I end up with 2/4 squared minus 2/4 plus 1. 2/4 is the same as 1/2, so 1/2 squared is 1/4 minus 2/4, and these are all in terms of fourths. So I'm going to rewrite that 1 as 4/4. Then we have 1 minus 2 is minus 1, plus 4 is 3. So we have the square root of 3/4, and the square root of 3/4 is the same as square root of 3 over square root of 4, which then is the square root of 3 over 2. So the distance between square root of 2 over 2, when x is square root of 2 over 2, and the origin is going to be the square root of 3 over 2. A little interesting in that one because we have a little bit more to work with as far as our square roots. We haven't done a whole lot of that as yet. Okay. So wrapping this up, last thing it says using a graphing utility to graph the function d equals d of x when x is greater than 0, rounding to two places, find the value or values of x at which d has a local minimum. Okay, and so what point over here if x is bigger than 0? So only paying attention then to this section over here, what is the closest distance we get then to the origin? So that's our question that we're asking. So let me go ahead and pull up my calculator here. I thought I had this loaded up. I apologize for that. And where is it? Well, had it in here a moment ago. Let's see if I can't find it. Did I put it over here? I know I've got it back over here. Whoops. All right, let's see if I can't find that. And all right, I think I found my item back again. And let me go ahead and grab that one more time. Okay, and now I think I've got it here. So I finally found it. That we have it, let's see what we wanted to graph. We wanted to graph this function. Let's pull it back up over here. So we want to graph this. And so if I go ahead and say I want the square roots, so we got the square root of x to the fourth minus, oops, I want to get out of there, minus x squared plus 1. I'm going to go ahead and see the graph. And so as this goes ahead and graphs in there, what we see then is that it doesn't seem to do anything. That means it's, oops, apparently I didn't have the right item in there. I'm not sure what happened there. Let's go ahead and do that again. So let's see, the square root of x to the fourth minus x squared plus 1. Now let's see the graph. Okay, now it's working. We see that over there. So there's our graph. And it looks like our minimum is going to be way over here down around between 0 and 2. So one of the things I want to do, so I'm going to go ahead and I'm going to adjust the window. I'm going to go from an x value of 0 to an x value of 3 and see how that does. And I'm going to go ahead and stretch this y values maybe from -1 to 5. Let's go ahead and see the graph. Yeah, now I can see that a little bit better. So we can see it's going to have a minimum somewhere over in here, a little bit less than 1. So how I can find that for sure, so I can do the second and trace commands and find the minimum, which is number 3. And so the left bound, I'm going to go ahead and keep moving over here a little bit farther left. Okay, so that seems far enough. So I go ahead and say, yep, that's my left bound, right bound. So currently my y value is at 0.89. So I'm going to go, that's 0.87, 0.6s, back up to 0.87, 0.8. Now increasing back up. So I'm going to say, let that be my right bound. And then just a guess there, anywhere we guess is fine. So our minimum value, it occurs when x is 0.71. Okay, so on that one, when we take a look at this graph again, this part up here, let's see, rounding two places, find the value at x that d has a local minimum. So on this one, we would say, part E, we have at x equals 0.71, the area, or not the area, this is distance, the distance is indeed smallest. Okay, and if we were asked, well, what is that distance? The smallest distance we come up with is 0.8660254, that value in through there. That is the smallest distance that we can get to this line, or this curve rather, y equals x squared minus 1 in the origin. Okay, so interesting question on that one. So incorporating some different ideas here using the graphing calculator, doing some transformations, or wrapping some things up from chapter 3. Take a look at example number 2. Let's do the area of a rectangle. And so we see from our figure here, we've got a rectangle, has one corner over here in quadrant 1 on the graph. So that point there's on the graph of what? 25 minus x squared. We've got another at the origin right here at 0, 0. Then we have another, the other 2 points are on the x-axis and on the y-axis. So whatever our x-y pair is here, the x is going to be also on the x-axis and the y will be on the y-axis. Interesting about this, wherever our x, y end up, then we end up with a rectangle. So if we have an x, y pair here, then our rectangle would be something like this. If we have an x, y pair over here, then our rectangle is going to be over here. So that rectangle is going to change based off what our point is on the graph of 25 minus x squared. So letter A asks us to express the area of the rectangle as a function of x. So if we want area of any rectangle, so the area of any rectangle is going to be the base times the height, or length times width, however you want to phrase that. So our base here and our height, well, our base is just whatever the x coordinate is over here. So the base is going to be our x, and our height is going to end up being whatever our y coordinate is. So we really end up with the area of our rectangle is now x times y. Now our question specifically asked us, though, to write this as a function of x. So that means then that when I write this area, I want to be able to write it in terms of x. I'm going to change my notation. I'm going to say a of x, so x is going to be my input. Well, x is going to be fine. My y value I need to rewrite. Fortunately, we're already told y is in terms of x is 25 minus x squared. So I can write x times 25 minus x squared here. Now I have a function of the area just in terms of x. Okay. Now, as we finish up the rest of this, we could go ahead and go on, and we can do letter B here. What's the domain of A? Okay, so there's our area function. We could, if we wanted to, we could expand that out or distribute the x and say that that is 25x minus x cubed. That's another way we could have written that function. Let's take a look at letter B, our domain. So in our domain here, let's see what we end up with. What we have is we have the area of this rectangle. So the area of the rectangle, know the area has to be at least positive, okay? Maybe could be 0, okay? So if it's 0, okay, that means that either we had a height of 0, or a width of 0 rather than, meaning that we were right here. So our x was 0, or out over here, our x was 5. That way our height is 0, okay? So since we have that scenario, we could have also, so we're going to say it's between 0 and 5, could have also said that y equals 25 minus x squared. That value has to be bigger than or equal to 0. So we could do this algebraically as well. Then I could say, let me just set it, yeah, I can do it this way. Set it equal to 0. So when does that go to 0? I'm going to figure out this value right here, and it should be 5. So if I move my x squared over, get 25 equal to x squared. If I square root both sides, then I get x equals 5, which indeed is that number. Now, technically an equation, if I do a square root, should be plus or minus. So if I would have extended this down, I would have been out here also at -5. However, since our graph is restricted to just quadrant 1, out over here, this -5 is going to be inconsequential. Doesn't make any sense, so I don't need that. So what we have then, our domain is going to be between 0 and 5. So we can say 0 to 5 this way, or we could have said we're between, x is between 0 and 5. 0 is less than or equal to x, which is less than or equal to 5. Letter C then asks us to graph area, which is a of x. Notice we got this icon up here, so we're not asked to graph this 25x minus x cubed just on our own. We're going to be asked to do that with a graphing calculator. So if I pull my graphing calculator back up and through here, Wait for it to wake up here just a moment. There we go. Go back to y equals. I'm going to clear this out. And let's say we have 25x minus x cubed. All right. And I'm going to go back to my window here. Actually, no, I'm just going to go ahead and graph this. And we see I've got from 1, 2, 3. Yeah, so that's not a great window to look at. So I can go back to my zoom, and let me do a zoom fit. So let me zoom or scroll back down here. Zoom fit is number 0, so I'll do number 0. So I can see a little bit more of what this graph of doing looks like. It's going to come up and then maybe come back down over here. So I'm going to expand that out. So what I'm going to do is I'm going to go back to the zoom, and I'm going to zoom out a bit. Oh, all right. So that gives me a good indication of what's taking place. So since I'm only in quadrant 1, I'm going to be interested in the material over here. So that's going to be our graph. And we want to figure out, well, what is the value of x when it's the largest? Okay. So when it's largest, we want to figure out, well, what is this spot over here? So I can go back to my second and calculation commands, figure out the max, which is number 4. And so I want to be on the left side of that, on the right side of that, and it's going to figure out that this is going to be my maximum value. So left bound over there, my right bound arrow over. Now if you have a handheld, this goes a little bit quicker. There we go. So I'm on the right side of that. And so in between those, I figure out that my maximum value is about 2.9. And when my x is about 2.9, then in this case, the largest area of the rectangle I end up with is about 48.1. Okay. And so where we're given any directions over here as far as where to round is what I'm going to take a look at. For values of x, what is a the largest? Okay, so a of, I think we said 2.89 works out to be our largest area, which is about 48.11. Okay, so when x rather is 2.89, okay, 2.89, then our area is biggest. So really what we have in our graph here, that's a little bit less than 3. So this is representative of then the largest area we can come up with. If we move this point up here, then we get slightly skinnier rectangle, not as big an area. Move down here, we get quite a bit wider rectangle, still smaller area overall. So this is going to end up being our largest area. So this particular question, area of a rectangle, trying to figure out in our graphs here, as we go ahead and graph, what does the graph look like? Can we come up with rewriting this in terms of only one variable? In this case, we only chose x. And then can we do some other graphs? Let's take a look at another example. This one's going to involve airplanes. Let's suppose two planes flying at the same altitude are headed toward each other. One plane is flying due south at a ground speed of 400 miles per hour and is 600 miles from the potential intersection point of the planes. The other plane is flying due west with a ground speed of 250 miles per hour and is 400 miles from the potential intersection point of the planes. See figure 72. Now, interesting on this one in my notes, for whatever reason, I didn't put in that figure. So let's take a look at it. If I do my normal directional values, normal directional values here, we would say we've got north and south, east and west. That's the normal item. So we've got a plane traveling, what do we say here, due south. So we've got a plane traveling this direction. We've got a plane traveling that direction. And so what we end up with then is a plane going here, plane going here, and we've got the distance between them would be that value. So what we also that we know is we've got a ground speed of 400 miles per hour, and we also know that this distance overall we were told is 600 miles. So the distance over here, so maybe if I put this in an XY grid then, something of this sort, so this is 600, so like 0 is 600. And this point over here, we know that we are 400 miles from the potential site. So that could be something like 400, 0. And this is traveling at 250 miles per hour. If we take a look at it that way, we say, okay, well, how are these planes getting closer and closer? We want to figure out D. Okay, So as we take a look at a model here, I can say, well, this is a right triangle, so I can employ Pythagorean's theorem. So d squared equals the square root of the horizontal squared plus the vertical squared. So we take a look at the horizontal. It starts out at 400. Whoops, don't need the d squared there. What I would have done here is, let me back up just a moment because I did have a d squared in there. I get d squared equals this horizontal squared plus the vertical squared. And if I only want the distance, I would do it this way. Okay. So now let's take a look at the horizontal square. That's what I was building into. So on this, let's see, the horizontal, I'm 400 miles away from the intersection, but I'm decreasing this distance because I'm traveling 250 miles per hour. So I can say minus, I guess I should say minus here, minus 250 miles per hour. That's a time component. So let's go ahead and say that's time. And then plus my vertical component, that was 600 miles away. And we're decreasing this at 400 miles per hour. So minus 400, let's say t squared. So now we have the distance, I guess I'm going to do it as a function, distance in terms of time. So here's a model then that relates these two items. If we want to go ahead and do part B, it says use a graph utility to graph the distance and then how close do the planes come together, okay? How close the planes come to each other and at what time does that happen. So we want to figure out what is the corresponding y value and what is the corresponding x value. If x is t, okay? So let's go ahead and go back to our graph. Whoops, back up over here. Let's go to y equals again. Wait for it to wake up here. Whoops, all right, just have to turn it on. So I'm going to go back to y1, so I'm going to clear this out. I'm going to say I've got the square root of, and I got a bunch of stuff in here. I got parentheses, and we got 400 minus 250. Now, I can't choose t, so in this calculator I can only choose x, and then I'm going to end up squaring that. There's my square button. And then plus, and then it was in parentheses 600 minus 400 x. Oops, I got 4,000. Don't want to do that. 400x, and then we'll square that also. So there's our graph, and if we go ahead in our equation, go ahead and graph this one here. Okay. Still have it set the previous item, so it looks like we have a bit of a an item that's coming down almost like a V shape or maybe a bit of a parabola here. Not quite sure really how I'd classify that because it's so pixelated on our view screen. But what we can do is we can still figure out what our minimum value is, so which is what we're interested in. So I can say a second trace, which is the calculation menu. So I can go up to number 3, which is a minimum. Left bound, let me go a little bit, oops. Let's say 1.3 is okay. Moving to the right a little bit. We get 1.6 is okay. And estimate a value, and we figure out that the minimum value here occurs when x is 1.5, or when time is 1.5. Our y value, which was the distance, is 21 points. If we round, it's 21.2. Okay. So how close do planes come together to each other? Okay. The distance. Closest distance, I should say, maybe closest distance is about 21, I think we said, what, 21.2? Yeah, 21.2. And this was miles apart. At time of, I think we said 1.5 hours. Yeah, 1.528 at 1.5 hours. Okay. So what we were able to do then is we could take a look at a model, put an equation involved with this back to a form that we're familiar with as far as the distance formula, and then we can calculate some other values based off of that. Okay. Last example in this section, geometry question here, kind of category. Let's say we have a wire that's 10 meters long. It's going to be cut into 2 pieces. One piece will be shaped into a square, and the other would be shaped as a circle. Take a look at the figure here. So what we have is we have this 10-meter piece of wire. We're going to use one piece of it. If we cut it here, use one piece of that and form a square. So when we form a square, this side is x, top is x, left is x, bottom is x. So the perimeter of my square is 4x. So however long this piece is here, it's going to be in terms of x, it's going to be 4x. What I have left over then is going to form the circle. So what do I have left over? If I have a whole thing here that's 10, and this top piece is 4x, what's left over is 10 minus 4x. I want to take 4x away from my 10. And then that's going to form my circle. And for my circle, I could say my circumference then is 10 minus 4x. When we talk about the distance around an object, if it's a polygon, we talk about the perimeter. If it's a circle, we talk about circumference. Okay? Well, what are we asked to do with this? Now we have a little bit more of a better impression as far as what we have. Letter A in our question asks us then to express the total area. Okay, so total area enclosed by the pieces of wire as a function of the side length x of the square. Okay, so let's take a look at that a little bit closer. Let's grab the pen. So what we want is total area. So total area will be the area then of the square plus the area of the circle. Okay? Well, the area of the square, if it's a square, the area of a square is the side squared, so that's going to be x squared. Area of a circle in general is going to be pi r squared. So what we need to do on this one is if we want this as a function of x, okay, so I want this to be able to write as a function of x. I only want to be able to write it with x's. Now, pi is a constant, so I can leave pi there. That's not a problem. But I need to figure out what the radius is of my circle. Well, fortunately, we do know from our top that the circumference is 10 minus 4x, and the formula for the circumference is 2 pi r. So what I want to do now is I want to solve this equation for r. So if I divide both sides by 2 pi, okay, now let's see, the 2's cancel, pi's cancel, r equals then. So I can divide everything by 2 and get 5 minus, let's see, 4 minus, or 4 divided by 2 is 2, x, and then over pi. So my radius, okay, there's my radius. So I'm going to replace that in here. So I got pi times 5 minus 2x over pi squared. So now that I have that one, that is an expression of the total area just in terms of my x. Okay. And if we want to, we could clean this up. We could expand that and simplify overall. Let's just go ahead and leave it in this format. Then letter B, what is the domain of A? Okay. What is the domain of our area? Okay. So our domain, okay, where our input is x. Now, when we do our input, when we take a look back at our original up here, x here was the side of the square. So, and in terms of our wire, the maximum length of the wire was 10. And so what we have as far as our 4x here has to be somewhere between 0 and 10. If we let x be 0, then basically what we're saying is that we have no square, and the entire length of this wire is going to be wrapped around into a circle. If 4x equals 10, then we're using nothing for the circle. We're using everything then for the square. And so that's why we can say this is going to be between 0 and 10. So to solve this, we'll divide all sides by 4. So 0 is less than or equal to x, less than or equal to 10 over 4 is 2.5. So our domain here is going to be between 0 and 2.5. So we write it that way, or I could write it in interval notation this way. Now part C says what is the, graph this, and what is the value of x that gives us the smallest area. Okay, so now we want to go back into our calculator, and our goal is going to be to go ahead and graph this shape and see what that gives for us. go ahead and turn this on. Let's go back to our y equals, clear that one out, and we've got an x squared, and then plus, I've got pi multiplied by, and then I've got 5 minus 2x squared all over pi. So I'm going to put another parentheses in here. So I've got 5 minus 2 times x. Take that divided by pi. Close off that set of parentheses. And then I want that squared. Okay, so that gives me this 5 minus 2x divided by pi, then the whole thing squared. What we want to do is we want to take a look at this. We know it's between 0 and 2.5, so I might just go to my window settings already. Say let my x min be 0. For the graph, let me go ahead and go to -1, just so we can have a little bit of more viewing. Take this out to 3, and let's go ahead and count by halves. Not sure where my y values are going to be, but let's go ahead and take this from 0. Let's see, let's take it out to 100, because if I had 10 squared, that would be 100. That was the area of the square. So let's see what we end up with that one. Let's go ahead and count by tens on this. Let's take a look at the graph. All right, and that didn't do much for me here. Maybe I had a different window setting. Let's see, what did I have? From negative, oh, my x max was a half. I wanted it to be 3. I messed up there. I wanted to go out to 3. And then I was counting by halves. That was my original intention. Let's fix that and go back to our graph here. There we go. And we see that it does kind of bottom out over in this region and starts turning back up. And so let's go ahead and calculate our graph here. It says calculate our minimum value. So that's number 3 here. Left bound. Yeah, somewhere over here is 3.9. If I keep going to the right, down at 3.6, 3.62, 3.58, 3.54, 5.2, 5.0, all back to 5.1, 5.2. So it's starting to count back up again. So once they start counting back up, let's go ahead and leave that. Press the enter key again, and what we end up with is we have a minimum value at about 1.4. And our area then, our max area, is about 8.5. Okay, so our minimum value is when x is 1.4. So let's see here on slide over here, letter C. Oh, get my pen back again. Letter C, a of 1.4 is the smallest area of approximately, what do we say that was, about 8.5. And this would end up being meters squared officially because our unit was in meters overall. Okay. All right, so that wraps up Chapter 3, Section 6. Let's move back up. Oops. Back at the beginning here. Let's see. Come on. There we go. What we're looking at was mathematical models building functions. So taking a description, can we go ahead and based off that description come up with a graph? Can we do some other items with it with our expressions and equations and all those sorts of things? So this also, for our college algebra course at Marion Technical College, our first midterm wraps up after this section, if I'm not mistaken. If I am mistaken, I'll make a correction in the notes as far as our modules and in a class announcement. But that does wrap up everything we need to know for our first exam. Okay, and exam details will be posted in Canvas, so make sure you watch out for that. As always, if you've seen a mistake in one of the things I did in the video, please go ahead and drop a line and let me know. That way I can fix it. Otherwise, I'll see you in another video.